Right, so in the previous video, we looked at proving that there were that root 3 was an irrational number, and we used proof by contradiction to do that. So today we're going to again use proof by contradiction, but this time to prove this example here. So prove that there are infinitely many prime numbers. So again, we're going to do a proof by contradiction to prove this statement. So again, proof by contradiction, we want to assume that the opposite statement to the statement in the question is true, and then we want to perform some calculations, do some maths basically, and then get a conclusion that contradicts our initial assumption. So what we're going to do here, again, a proof by contradiction. So we're going to assume to the contrary, so assume to the contrary that there are, so that there are finitely many prime numbers. So finitely many prime numbers. Okay, so if there are a finite number of prime numbers, then let's just assume that there are n prime numbers. So assume that there are n prime numbers where n is a natural number. So assume that there are n prime numbers. So we're going to assume there are n prime numbers in the universe, so n primes. So P1, P2, prime 3, prime 4, prime 5, prime 6, all the way up to prime n to Pn. So you've got a finite number of primes. Okay, so now the trick to do this proof is we want to call capital P, I'm going to call it capital P, let capital P, unfortunately this is just a trick that you need to learn. I'll use like straight lines to use this to draw the capital P. So capital P is equal to P1 times P2 times P3 times all the way up to Pn plus 1. So I'm going to call capital P this number here. So all the primes times together, add 1. So we've got this number here. Now, either this number here is a prime number or it's not a prime number. So either a number is prime or a number isn't a prime number. So either case 1, this capital P is prime, or case 2, P is not prime. Okay, so we've got these two cases here. Let's think about case 1. So if case 1 is true, so if P is prime, then that's a contradiction. So this is a contradiction. So why is case 1 a contradiction? Well, because we assumed at the start that there are n primes. So these are all the prime numbers in the universe: 1, 2, 3, 4, 5, 6, 7, all the way up to n. So we assume that these are the only prime numbers in the world. So the only prime numbers that exist. Yet, if our case number 1 is true, that contradicts that initial statement because we just assume that there are n prime numbers, and now we've created a new one. So case number 1 is a contradiction because we've assumed. Sorry, let me type or write a little bit better. So we've assumed that P1, P2, P3 up to Pn are the only prime numbers, are the only primes. But if, again, this capital P is prime, then that contradicts that. So let's look at case number 2 then. So case 2, P is not prime. So if a number is not prime, that means that there must be another number between 1 and itself that goes into that number. So, for example, the number 9 is not a prime number, and that's because obviously 1 goes into 9, 9 goes into 9, but there's a number 3, which is between 1 and 9, which goes into it, so therefore 9 is not prime. So if P is not prime, so if this capital P is not prime, then there must exist, so then there exists a number, and we'll call this number K. So there exists a whole number, so a whole number K, which is an integer, so a positive integer K, such that such that P divided by K is an integer. Because again, think about it. A number that's not prime, for example, again, the number 12, there must be a number between 1 and 12 that goes into 12 because 12 is not prime. So let's pick the number 3. Well, if 3, 3 goes into 12. So P divided by 12, so sorry, 12 divided by 3, the number you picked, is obviously a whole number as well because, again, 12 is not a prime number. So basically, yes, there must exist a number, K in the integers, and this K must be between 1 and P. So 1, K is trapped between 1 and capital P. So it's got to be a number between 1 and P, a whole number, such that the big P, that this number here divided by this number gives us another whole number, because that's what it means for a number not to be a prime number. So there must be this number, and in fact we know that we know for a fact that any number, because we would have seen this at like school maths, high school maths, secondary school maths, is that you can write any number as a product of prime numbers. So that means that there must exist a prime number that goes into K. There must exist a prime number that is a factor of K. So therefore, there exists a there exists with an S at the end. There exists a prime number. Let's just call that prime number P. Let's call it P. I don't know, Pi. So there exists a prime number Pi that is a factor of K. So again, think about it. So pick any number you like. There must be at least one prime number that goes into that number. Pick the number 10, for example. So 2 goes into 10. 2 is a prime number. So there we go. There exists a prime number that goes into the number you picked. So pick any positive whole number. There must be a prime number that goes into that number. So in this number K that we're dividing the capital P by, there must be a prime number that goes into it. So therefore, P, this capital P divided by this prime number must also be an integer. So that must also be an integer as well. So that is also an integer. So this is where the contradiction is going to come into play. So we know that that must be an integer. If our assumption is true, that must be an integer. I'm just going to move this across here. So, okay, we've got P is equal to the product of all our prime numbers plus 1. Okay, so let's think about this. We've got 1. If we take away, if we again write this equation again, so we've got capital P is equal to P1 times by P2 times by P3 times by all these other prime numbers up to Pn plus 1. So therefore, that means that 1, the number 1, is equal to capital P take away P1 times P2 times P3 all the way up to Pn. I've just taken away this number here from both sides of the equation to get 1 equals capital P, take away that there. So what we can do then now is again divide both sides by this prime number, this Pi prime number. So let's do that and let's see what we get if we do that. I'm just going to try my best to make my writing smaller. There we go. Something like that. There we go. So then, okay, so we know that P divided by Pi must be an integer because this prime number must go into capital P. So therefore, yeah, if we divide everything by P, so therefore 1 over Pi equals P over Pi, take away P1, P2, P3 times ... Pn over Pi. Now the key thing is that Pi is one of our prime numbers. So Pi is in the list P1, P2, P3 ... up to Pn. So we've assumed that there are a finite number of prime numbers. These are the only prime numbers in the universe. So Pi must be in that list. Like it must be one of those prime numbers. So that means, yes, we know that this capital P divided by Pi, well, that must be an integer. So that's going to give an integer because again, we know that this Pi must be a factor of this capital P. And now because Pi is one of these prime numbers in this list, that is going to this pi is going to cancel out with some pi somewhere in these ... somewhere. So that, because obviously again pi is one of those numbers in the list, pi divided by pi is the number one, the pi will cancel out somewhere. So again, you're going to get an integer. So this fraction here turns into an integer. So the pi must go into that product, because again, the pi will cancel out with the pi on the numerator. But now on our right hand side, we've got an issue, because 1 divided by this prime number, remember all prime numbers are bigger than 2. Let's just make a note of that pi must be bigger than 2, bigger than 1, sorry, my bad, because obviously the first prime number is 2. So pi is a number bigger than 2, bigger than 1. 1 divided by a number bigger than 1, well, that's going to be a fraction, and that's not an integer. So not an integer. So we've got a problem here. We've got an integer here, take away an integer here. Obviously, when you do an integer, take away integer. So integer, take away integer. Obviously, that must be a whole number. Whole number, take away a whole number gives you a whole number. It's never going to give you a fractional number. But we've got a number on the left-hand side, which is not an integer. This is a contradiction. So therefore, we have a contradiction. This is a contradiction. So therefore, there must be infinitely many primes. So this assumption at the start assumed that there are finitely many primes. I mean, our assumption can't be true then, because if it were to be true, we get these two contradictions in case number 1 and case number 2. It's impossible. So therefore, there are infinitely many primes. So there are an infinite number of prime numbers. That's what the proof is telling us. And that's the end of that proof. Yeah, so again, another proof by contradiction example, where you want to assume to the contrary that there are a finite number of prime numbers, and then you can look at these two cases where this capital P number, so you want to times all your primes together, add 1 to it. You've got two cases. Either that's a prime number, in such case you've contradicted your assumption, and if capital P is not prime, then you can find a prime number from this list of prime numbers P1 up to Pn that goes into the capital P. And obviously this prime number Pi, we called it, must be in the list P1, P2 up to Pn. So we get, when we do the maths over here, we see that we get an integer on the right hand side of that equation, but not an integer on the left hand side. There's no way that a fraction could be equal to a whole number. So yeah, we get a contradiction. So that's how you'd prove that there are infinitely many prime numbers.